Hi AP Chem. This is section 6 of chapter 5. This is Kinetic Molecular Theory, KMT for short. Gonna cover some of the theory behind gases, gonna cover root mean squared velocity and kinetic energy. You also have a worksheet that you'll be doing and reading this stuff too, so you'll be reading it on your own. You're going to be listening to me, aren't you? And, yep, nothing more needs to be said on that one. Ideal gases. Gases behave ideally at low pressure and high temperature, and you'll find out in the next video they actually behave ideally in low concentrations. So here's what I'm going to do. I'm going to write that down. I would advise you to write it down also. Gases behave ideally under 3 conditions: low pressure, high temperature, and actually low concentration. What's the main focus of all these 3 variables? The idea basically behind ideal behavior is the fact that the gas molecules themselves, the actual itty-bitty thing, will not contribute to the volume. It's mostly empty space, and experience attractive forces. Will not. Now you think about it logically, these variables will achieve these goals. Low pressure means high volume. That means that you are going to have gas particles just spread out all over the place, not even knowing the other particle is in existence, let alone being attracted to it. High temperatures, they're going to be moving so fast, they're never even going to be able to run across each other. They're moving so fast. Ships passing in the night. And in low concentrations, it's the same idea. There's so few molecules in the sample, they're not coming across each other to contribute to the volume or be attracted to each other. All right, kinetic molecular theory. The volume of the gas is mostly empty space. The actual particles of the gas is practically zero. The particles themselves do not contribute. Gases are in constant motion. Pressure is measured by how many times and how hard the little gas particles hit the wall of the container. Gases exert no forces on each other, neither attractive nor repulsive. And most of the time they're talking about no attractive forces. Because guess what happens to the volume of a gas if the molecules of the gas are all attracted to each other and you got this one big glob of gas particles all attracted to each other? They're going to contribute to the volume and everything gets messed up. Temperature in kelvins is equal to kinetic energy. What does that mean? Temperature is a measure of motion. Temperature measures kinetic energy. Kinetic energy is the energy of motion. The faster something moves, the hotter it is. All right. Some of the equations that go along with this section, and most of it's going to be plug and chug. Average kinetic energy of a sample of gas. Average kinetic energy is going to be 3/2 RT. Now, a couple of questions I want you to answer. Question number 1. Do you see that the mass of a gas has any bearing on the average kinetic energy? Just look at it. Mass does not contribute to kinetic energy. Only temperature. Only temperature. That means if you have 6 samples of different gases at the same temperature, they will have the same average kinetic energy. The only variable in this equation is temperature. Because of course R you should recognize. Now, R is going to be a different R than the 0.08206 liter atmosphere mole Kelvin. Why? Because we're talking energy. You need an R that's energy units. 8.3145 joules per Kelvin mole. And the other one gets converted, blah, 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 blah. Bottom line, the new R, anytime you do average kinetic energy or root mean square velocity, anytime you're calculating the energy, 8.3145 joules per Kelvin mole. Temperature in kelvins, of course. Kinetic energy will have units of joules per mole. That J you came across first year chemistry. That is the joule, or kilojoule is another option. And that is the units of energy. Kinetic, potential, energy. And we need the different R because you're dealing with units of energy. So we need the 0.08206 liter atmosphere mole Kelvin ain't gonna cut it. We need the new R, 8.3145 joules per Kelvin mole. And again, pretty much a plug and chug. The only variable you got staring you in the face is temperature. Root mean square velocity of a gas. Root mean square velocity is the square root of 3RT divided by molar mass. Now again, the energy R, that's what I call it. Use the energy R. Gas laws, it's the other R, 0.08206. Root mean square velocity and kinetic energy, 8.3145. Temperature in kelvins, that's been the gospel since we started this chapter. Now here's the kicker. Molar mass in kilograms. Okay? And I'm going to explain why. Units for root mean square velocity are meters per second. Velocity, speed, distance over time. In the metric system, distance over time, meters per second. So root mean square velocity is meters per second. Now, here's the problem. How do we get units of velocity for root mean square velocity when we're dealing with R, which has units of joules per Kelvin mole, and Kelvin, and mass in kilograms? Where does the meters per second come in? I'm going to tell you. We have the root mean square velocity being equal to 3RT over molar mass in kilograms, square rooted. Molar mass, capital M, same diff. All right, just in terms of units, your R is units of joules per Kelvin mole. Your temperature is in units of Kelvin. The molar mass has to be in units of kilograms per mole. Okay, so Kelvin cancels, mole cancels. I'm left with joules per kilogram. And it's still in the 1/2 part. I'm just dealing with the units. A joule is a kilogram meter squared second squared over kilogram. The joule is kilograms meter squared second squared. Now notice the kilogram's going to cancel. So you basically have, after all this manipulation, meters squared over seconds squared square rooted, which of course is the meter second. What, Mrs. G? Are you out of your mind? No, what I want you to realize is velocity is units of meters per second. That's why the mass has to be in kilograms per mole and not grams per mole, because all this cancels out, so that your bottom line is when you calculate root mean square velocity, you get meters per second. All right, examples. First example. Calculate the root mean square velocity for the atoms in a sample of helium gas at 25 degrees Celsius. Root mean square velocity. And again, root mean square velocity and kinetic energy is pretty much a plug and chug. Just be careful. The equations are given to you on your formula sheet. All you got to do is put things in the right units and put it in the right spot. All right, my molar mass has to be in kilograms per mole. My R is the 8.3145 joules per Kelvin mole. My T is, of course, temperature in kelvins. So before I plug anything in, I'm going to make a couple of comments. Helium has a molar mass of 4.00 grams per mole. I'm going to rewrite it. Grams per mole. I need to convert it to kilograms using dimensional analysis. There are 1,000 grams in a kilogram. Lo and behold, if that's not going to be 0.00400 kilograms per mole. My temperature has to be in kelvins, which is going to be, of course, 298 kelvins. And my R has to be the 8.3145 joules per Kelvin mole, which, of course, remember, is going to be given to you. This is on the formula sheet. This is on the formula sheet. You can't miss. Right? Plug in your numbers. 3 times 8.3145 joule per mole Kelvin times 298 Kelvin divided by 0.00400 kilograms per mole. I get square root of 1.86 times 10 to the 6th in units of joules per kilogram. Now, again, just to bring it on home, 1.86 times 10 to the 6th in a joule is a kilogram. Meters squared, seconds squared, kilogram. From there, kilograms cancel, square root the whole darn thing, and you should get 1.36 times 10 to the 3rd meters per second, because those are your typical units for velocity. So either remember that a joule is a kilogram meter squared per second squared, or just flat out remember that root mean square velocity is in meters per second. Now, root mean square velocity does depend on mass, unlike kinetic energy. And it's opposite too. Look at the math here. Root mean square velocity is the inverse of mass, which kind of makes sense too, because really, the fatter the molecule is, the slower it's going to be. So, second example. Again, another plug and chug. This one wants you to calculate the average kinetic energy, oh, and the root mean square velocity of nitrogen and carbon dioxide in this room. Okay, temperature in this room right now is 21.0 degrees Celsius. Whoosh. All right, average kinetic energy. I'm going to make two columns. Nitrogen, molar mass, 28.01 in grams per mole. Carbon dioxide, molar mass, 44.01 grams per mole. And I'm just going to make this right down the line. What do you want to do first? Let's do kinetic energy. Kinetic energy is 3/2 RT. That's going to be 3/2 8.3145 joules per mole Kelvin. Temperature being 294.2 Kelvin. Kinetic energy for the CO2 is going to be the same. How come? Kinetic energy is not dependent on mass. You are going to get exactly the same thing for kinetic energy. 3.669. Why so many sig figs? 1, 2, 3, 4. That's why. Times 10 to the third joules per mole. Kinetic energy over here. Same math, same numbers, same answer. 3.669 times 10 to the third joules per mole. As long as they are at the same temperature, they will have the same average kinetic energy. Done with that. Root means square velocity. Square root of 3RT divided by molar mass. Now I'm going to make a theory here. I'm going to suggest that he is going to be faster because he is lighter. So let's see. 8.3145. I'm going to drop the units because I am so running out of room here. 294.2 molar mass, 1, 2, 3 places to the left, 02801 kilograms per mole. Root mean square velocity for the fat guy, 8.3145, same number, same temperature, different molar mass, bigger molar mass, 0.04401 kilograms per mole. Root mean square velocity for the nitrogen, it's going to go 511.8 meters per every second, and the carbon dioxide is going to be 408.3 meters per second. So yeah, faster, went further, farther in the same time frame. 1 second. So the nitrogen gas is lighter, and the nitrogen gas is faster. If gas molecules move so fast, I mean, think about it, 500 meters in 1 second, that's pretty good. Why does it take so long for them to get from one place to another? If I open a perfume bottle in the back of the room, why does it take so long for that smell to waft up to the front door? Gas particles should, theoretically, move in a straight line. But, problem is, you're in the room where there are 9 other gases, and not to mention all the other stuff in the room. You have sinks, and you have glassware, and you have tabletops, and you have desks, and you have people. Gas particles can only move in a straight line if they're in a vacuum. So any gas particle will have to go bouncing off everything in its way. Bottom line, gas particles can't move in a straight line because there's too much stuff in their way. So they have to bounce off everything. And that's the end of this one.